properties of matrix operations. Basic properties of matrices would align themselves with the basic properties for real numbers, with the exception of multiplication of matrices. Matrices do not commute. So we cannot say that A times B is equal to B times A, where A and B are matrices. You can do that with numbers, but not with matrices. So um, uh, we still talk about the associative property for addition and also multiplication, uh, the community property for addition. Uh, with multiplication, it has to be strict left distribution law and strict right distribution law. So parts E and F are not equal because A times B is not the same as B times A, and neither would AC equal CA. So now part B is kind of close going to um, the idea of commutativity, but it's not commutativity. It's just multiplication uh, with the property of associativity. And so it doesn't matter where you put the emphasis on, as long as the as the order is in place. The arrangement. If A is on the left side of B, and likewise B is on the left side of C, then even on this right side where you have A times B in parentheses times C, that order is still preserved. So this section just deals with just some very basic properties, nothing extraneous. Now for parts G, H, and I, the small numbers denote scalars, and so the capital letters denote matrices. So we could talk about scalar distribution of a number being multiplied to the sum of matrices, which is G, or a number, a scalar, being multiplied to the product of matrices. It doesn't matter about the scalar in terms of where it is, you still get equality, but it does matter if it's a grouping of matrices being multiplied, and particularly the grouping um, A times B and B times A. We saw that in the previous section where we had a couple of matrices where that didn't work out to be the case. Common matrices, there are two: the so-called identity matrix, and I think I've probably made mention of that a couple of times before, and if you haven't had matrices, you're probably scratching your head, and so I did that on purpose to get you to this day. And we'll talk about what that is, the identity matrix, and then also the zero matrix. Very similar to numbers, you have just the zero element in numbers, but then in matrices we have the zero matrix. In numbers we have the so-called multiplicative identity of one. In matrices, that multiplicative identity is called the identity matrix itself. Um, so let's see. So just some common examples of zero matrices. The subscript just denote the size of the matrix. Here they are square matrices. So this is the zero matrix of size 2 by 2. Over here is the zero matrix of size 3 by 3. The identity matrix is a square matrix, coefficient matrix, with ones along the main diagonal and zeros elsewhere. Let's see. So there, the identity matrix uh, of the two space, and then the identity matrix for the three space. Again, you see the ones along the main diagonal, and then you have zeros elsewhere. We call those the identity matrix. Now here are properties for the transpose. We introduced the transpose um, in the previous section. Here are the properties. Let A and B be matrices of the same size. Then here part A says the transpose of a matrix A is equal to A. And that just makes sense. If the transpose is nothing more than the interchange of rows and columns, if you do that twice, then you get back to the original matrix. Part B, the transpose of the sum of the matrices is equal to um, the sum of the transposes, and likewise the difference follows suit. Here, part C says if you have a scalar times a matrix, and if all that's being transposed, then that's equal to, there's nothing defined as, in this case, a scalar transpose. Um, the transpose is only applied to the idea of a matrix. So the scalar just pulls out, and all you have left is just the transpose of matrix A. Now, part D is probably the strangest one. The transpose of A times B is exactly uh, B transpose times A transpose. You can't write that as A transpose times B transpose. I wish we could. You can work that out as an exercise. You can take a matrix A, a matrix B, and work that and see what happens. Matter of fact, I think we have a problem here in this section where I would do just that. And then for the homework assignment, I'll let you do that as well. We can talk about some applications of the transpose of a matrix. One is called a symmetric matrix. It's just defined as when the matrix itself A is equal to its transpose. So A transpose equal to A, then we say that A is symmetric. The matrix may be skew symmetric if if the transpose of A is equal to the negation of A. And I think we have a problem with respect to those definitions as well. Well, let's look at some problems. So here, the objective is multiplying a scalar times a matrix. So this is negative 3 times the first two matrices, and then add the corresponding parts, minus 2 times that last matrix, and then we combine the corresponding parts. Let's take that first part. So we're just going to multiply negative 3 times that first matrix. So we do, we get 0, 15. I tell you, every time for the first time, and that's the thing, I've been on this computer and I've done some other assignments and it didn't jump like that. I guess I hadn't been doing it for a while. I guess it wants to jump. I don't know. Um, you pray for patience, and this is what happens. So you can't curse, right? But anyway, so this is 15. Negative 3 times 8, negative 24, and then negative 3 times 2 is negative 6. So we're going to add that to negative 3 times, look, the negative 3 is in parentheses, and both of these matrices are in parentheses. So it's negative 3 times negative 6 is 18. Negative 3 times 5, negative 15. Negative 3 times 9 is negative 27. Negative 3 times 1 is negative 3. We close that up. Now, this is just negative 2 times everything inside. So I'm going to put a plus here and just multiply each term inside of the matrix by negative 2. So this is a negative 6. This is a positive 6, negative 16, and a positive 14. So now we add the corresponding terms. 0 plus 18 minus 6 is 12. 15 minus 15 is 0 plus 6. Even I can do that, right? It's 6. Negative 24. Lost my negative. It's negative 3 times 9 is negative 27. And I think I heard you say something too. Even through the internet and through time, you were saying that's supposed to be a negative 27. Yeah, right. Shut up. No, I'm just teasing. Thank you. Okay, remember I give you a D when this is over. No, I'm just teasing. I give you an A. So this is negative 24 minus 27 minus 16. What is that? Well, that's the answer over there, right? Negative 67. Well, okay, negative 24. I have to check my work. I have students doing that, and they check and say, "Oh, you were wrong on number three," and I'm like, "Yeah, shut up." But no, I have to go back and correct it before I retire. So this is 2, 3, 4, 5, 6, negative 67. Never trust the answer. All right. And then negative 6 minus 3 is negative 9 plus 14. That's the 5. Okay. If two witnesses agree that our word should be established, so that's the answer over there, then that's my word over here on the left side. So I guess it's true. Okay. So now, this was going back to that property. We want to verify just a lot of busy work in this section. The previous section, again, just busy work. Nothing really extraneous. I think we'll do a little work when it comes to the section on inverses, especially for a 3 by 3. But again, even that's busy work. This busy work. So nothing hard. You can do it. So what we want to do is to verify that the transpose of AB is the same thing as B transpose times A transpose. Well, what we have to do is first find A times B. Right? So let's see. A times B. I'm going to write it over here. Let's check. This is a 2 by 3. It's a 3 by 2. So we're going to get a 2 by 2. Not a plank, you know. Hey man, 2 by 2. Okay, yeah, right. Um, so it's always for the first matrix it's rows, second matrix times its columns. So this is 6 and 1, that's 7 minus 8, negative 1. And then this row times this column, so that's 0, 8 plus 8, looks like a 16. Okay. And then we move to the second row, first column. So this is negative 40, 8, 0, 1, negative 47. Then the second row, second column, 0, 0, negative 1. So that's A times B. Now let's find A times B transpose, which is just this matrix transpose. So to transpose, we just interchange the rows and the columns. So this first row becomes the first column, and the second row becomes the second column. So that's A times B transpose. So now we need to find B transpose and then A transpose. Okay. So let's see. B transpose, well there's B. So B transpose, this is negative 6, 0, 1, 1. 1, 8, excuse me. And then this is 1, negative 1. So the rows become the columns. And then A transpose. So here this this row becomes the first column, negative 1, 1, negative 8, and then 8, 0, 1. So now we need to multiply B transpose times A transpose. So B transpose is negative 6, 0, 1, 8, 1, negative 1 times A transpose, negative 1, 8, 1, 0, negative 8, and 1. And hopefully when we get through, we get this guy over here. Well, let's see. So it's a 2 by 3 times a 3 by 2, so we should get a 2 by 2. So it's this row times this column, so this is 6, 1, that's 7, minus 8, negative 1. Well, we got 25% right so far. So now this is this row times this column, so this is negative 48, 0, and then 1, negative 47. Well, that's good over there. This is 0, 8, plus 8, 16. It says 0, 0, negative 1. Well, we look there. Well, they're the same. So we can indeed conclude that AB transpose is indeed the same thing as B transpose times A transpose. Now here's what you can't say. Uh, we, and I'm going to write it in the correct way, that the transpose of AB is not A transpose B transpose. Now I'm going to have, we're going to have Freddie. He's going to try to do that on the test, you know. And do y'all watch the wrestling SmackDown? Well, that's what it's gonna. So that's what's gonna happen in class. No, I'm just teasing. I'm really a nice guy. Let's see, Freddie, you better do the right thing. I left a blank page because I thought it was gonna take a while to do all that. Make sure I did I satisfy all the questions for that particular problem. Yeah, just verify that AB transpose is the same thing as B transpose, A transpose. We did that. Okay, so now for this one, we have A transpose times A. You want to find that, then find A times A transpose um, given the matrix A. So let's see, A transpose is 2, 1, 0, 4, 2, negative 1. So now we multiply A transpose times A. So let's see, this is a 3 by 2 times a 2 by 3. So the result is going to be a 3 by 3. So is this row times this column. So that's 2 times 2 is 4. And then plus 1 times 1. So that's 4 plus 1. We get 5. It's this row times this column. So just this row times that column. You see it? So that's 0 and a 4. This row times this column. So that's 4 minus 1 is 3. This row times this column, 0 and a 4. This row times this column, 0 and 16. This row times this column, 0 and negative 4. Now the last, this row times this column, that's 4 minus 1 is 3. This row times this column, that's 0 and negative 4. This row times this column, that's 4 plus plus 1. 4 plus 1 is 5. All right, so that's A transpose A. So now we need to find A times A transpose. Where's A? There's A. 2, 1, 0, 4, 2, negative 1. And A transpose 2, 1, 0, 4, 2, negative 1. This is a 2 by 3, 3 by 2. Those numbers are the same, so this is going to be a 2 by 2. So it's this row times this column, so that's 4, 0, and so 4, 0, and 4. That's the 8. This row times this column, that's 2, 0, minus 2 is 0. This row times this column, that's 2, 0, minus 2, that's a 0. This row times this column, that's 1, 16, that's 17, plus 1, that's 18. So, now it's asking the question, are these matrices or the products symmetric? So let's see. So we have A transpose A, and then we take the transpose of that. I'm just looking at it over here. This is the results. I'm going to transpose that, interchange the rows and the columns. So this becomes 5, 4, 3, 4, 16, negative 4, 3, negative 4, 2 close, 3, negative 4, and 5. Well, that looks like A transpose times A. So this guy, A transpose A, is symmetric. So S looks like an 8. So A transpose times A to be transposed is equal to A transpose A, then that means that A transpose A is symmetric. Now the question in terms of A times A transpose, and then we take the transpose of it. So let's see, A times A transpose. Oh, I put that up there. I think this is 8, 8, 0, 0, 18, I believe. Yep. This is 8, 0, 0, 18. So we interchange the rows and the columns, we get the same thing. 8, 0, 0, 18. So this is equal to A times A transpose. Thus, A times A transpose is also symmetric. Now for the powers, here, for the powers of a matrix, and if that matrix is a diagonal matrix. What is a diagonal matrix? A diagonal matrix is a matrix with entries along the main diagonal and zeros elsewhere. That's very easy. A diagonal matrix is a matrix with entries. Doesn't matter about what those entries are, but they're entries along the main diagonal, and you have zeros elsewhere. If you take the power of it, all you do is just raise the power of the terms on the main diagonal. So here, this negative 1 raised to the 16th power, it's an even number, so that just becomes 1 positive. And I'm going to first go down the main diagonal, then I'm just going to put zeros everywhere else. 1 raised to the 16th power is 1. Again, negative 1 raised to the 16th power. Since it's the even power, then all these terms are positive. Now, like on the test, I may have, like, say, the example of 2, but it won't be raised to the 16th power. My goodness, you'll be there, without a calculator trying to figure that out for a while. But it may be number 2 here, or, negative 2, 1. And so then we may say a raised to the third power, so you can get those. Now, zeros elsewhere. I don't know why I'm seeing zeros show up somewhere else. I know I just had eye surgery. I had 5 eye surgeries. And so I do see some strange things. I don't want to tell my eye doctor because that may mean I may have to have another surgery. But no, I do tell him. My wife will say, why? How come you didn't tell your doctor? And then if I say I didn't want to have another surgery, and she'll say, well, you're just really stupid. So now, determine whether the matrix is symmetric, skew symmetric, or neither. A square matrix is called skew symmetric when A transpose is equal to negative A.